Session with the final lecture in Katarzyna Grabowska's mini-course on geometric mechanics.
Thank you very much. Start with somewhere in the middle of this diagram. What we did, we arrived to the generalized Tulczyjew triple, which means that we started to consider mechanics on algebroids. With an example of mechanics on Lie algebroids, and I will remind you shortly what it was. So we have, maybe I'll skip the definitions of Lie algebroids, but come to this diagram when we first defined algebroid in 5 different ways, and there were 2 ways that are of interest here. One of them was that an algebroid, a Lie algebroid, is a Poisson bivector, linear Poisson bivector on E star, and from this bivector I can construct a map. And the other definition, this definition with number 4, was that an algebroid, a Lie algebroid, also can be defined as a certain double vector bundle morphism that resembles the Lagrangian side of the Tulczyjew triple. And then I put together those 2 definitions and write a diagram with left-hand side being Hamiltonian, right-hand side being Lagrangian. And the idea is to generate the dynamics, the phase dynamics with solutions being curves in E star. And it can be done from Hamiltonian side or from the Lagrangian side in the same way as we did for the classical situation with our vector bundle being the tangent bundle. So we can take the differential of the Hamiltonian, map it with this map associated to Poisson bivector, and we obtain the first order differential equation in the middle. And then in this case it is always a vector field, just because the structure of this Hamiltonian side of the triple is like that we start from a section here and we land with a section here. These arrows are in the opposite direction, but in the canonical case we have isomorphism, so the direction of the arrow is customary in a sense. And here the direction is well defined because it is a map this direction, and in the opposite direction it isn't a map. And on the Lagrangian side we start from the section of this bundle. The procedure is the same. We take the image of the differential and then map it into the middle part of the triple, but this time what we can obtain can be an implicit differential equation, because we have a section of this projection and not of this projection. Sometimes it is a section of both projections, and this happens when the map lambda is 1 to 1. Then this image here is also an image of the section of the other projection. Okay, and so this is the reminder, and we were about to present examples. We finished with the question, do we need this? And there will be 2 examples. First example will be living on Lie algebroid, and this is just another way to look on the system which is very well known. The system, mechanical system on a Lie group with invariant Lagrangian, in a sense totally invariant. So it just does not depend on the point on the group. It depends only on the Lagrangian, depends only on the velocity. So we can write this Lagrangian on the Lie group. We can trivialize the tangent bundle, and we can write this Lagrangian only on the Lie algebra. And our system on the Lie algebroid, this extreme one being just algebra over one point manifold, will come as a reduction from the full dynamics generated from this classical situation with manifold being Lie group. So what do we get? Now, without looking at the reduction, we just know that this is a Lie algebroid. Therefore, it can be written as a map from T star G and to TG star, a map which is a double vector bundle morphism. This double vector bundle that is here is very special. This double vector bundle has trivial core. It has only projections here. And this double vector bundle has one projection which is trivial, and there is a core somewhere here. The anchor map is trivial in the sense that it maps everything to the zero vector. And since it is a representation of a Lie algebroid, there is the identity on G star. And to see what this map is, really, we will write it down in the trivialization. Of course, this is a linear space. It is a vector space. So T star of a vector space is just a vector space times the dual. Yeah. So this is in the trivialization. You can see that here are those projections marked in color. So this G star is just this G star. And this G is just this G, and there is really no core of this vector bundle. And what is the map? You take an element of the algebra, you take an element of the dual, and the map should be the identity over G star. So this element of the dual appears here, and here we have the information of the structure of the Lie algebra encoded in the dual of the adjoint map. So something about the bracket is here. As a matter of fact, everything about the bracket is here. And we can use this structure to generate the dynamics from Lagrangian, which initially was completely invariant and was, as a consequence, written on the Lie algebra. We take the differential of the Lagrangian and we compose it with epsilon, and we get the dynamics as written here, which means that the curve in G star should satisfy this this equation. We can write it as an equation for a curve in the Lie algebra. What we will get is exactly Euler-Poincaré equation here. And how do we obtain this this map? We reduce. So we start from Tulczyjew. There is one T missing here, so another mistake to correct. It should be T star TG in this place. So we start with the Tulczyjew map, and we trivialize iterated tangent and cotangent bundle, getting some products. Then we look how this map looks like in the trivialization, and then we reduce. On the Lagrangian side here, this reduction is really a reduction. So this is a symplectic reduction here. We choose the appropriate coisotropic submanifold. This coisotropic submanifold is putting 0 here. This comes from the condition that Lagrangian is invariant with respect to the group action. This means that if I differentiate this Lagrangian, I will land in such elements in T star TG that have, after trivialization, 0 here. So, yeah.
Right or left invariant?
Left.
of course, I mean,
we can just translate it, but everywhere here I used left invariance and left trivialization.
Consequently, yes.
Consequently, yeah. So if I translate it to right, some signs will be changed, but the result at the very end will be analogous.
Okay. And here we have just the projection, so we just cancel this dependence on, and there it should be G here. So you just cancel the projection, you just cancel this dependence on G, and it means that you forget about X, and what you get is a map. As a result, I started from the map here, and I landed in the map in the opposite direction, but it is as it should be in this case. Okay, so this is my first example. Although the system is very well known, this procedure of reduction was really not written anywhere. So I asked one of my students to do that as his master thesis, and this is the result of his work. Okay, and another example will be mechanics on a skew algebroid. So now our playground will be a vector bundle with, we may think, a bracket or a map or on a bivector on the dual, which is skew. This bivector will be skew symmetric, but will be no Jacobi identity. And such a system can be constructed out of, no, we could start with any Lie algebroid, or in the classical case, we could take just Tm and constraints, which are a subbundle, linear subbundle, which is not a subalgebroid. It means that it is not closed with respect to the bracket. People tend to call such constraints non-holonomic constraint. And there is, of course, a discussion, what does it mean to be non-holonomic? Is it enough to be just non-integrable? Some people say that to decide what is really a non-holonomic constraint, you should look at the variational principle and not only on the space of allowed velocities, but also on variations that are admissible, and then decide. But we will forget about this for now. So we will take just a subbundle, which is not a subalgebroid, and there is some restriction for type of systems that we can treat. We will be treating only so-called mechanical Lagrangian. So the very usual type of a Lagrangian, which has two parts. One is kinetic energy and one is potential energy, and kinetic energy has to come from the metric. So there will be a bundle metric here. So if we are on Tm, it will be just the metric on M. If we are in more general algebroid setting, we need a bundle metric, so bilinear symmetric positive definite form on E. Then we can write such a term which plays the role of kinetic energy, and there is a potential which should depend only on point on M. This potential cannot depend on velocity really, because this crashes, the structure crashes. We cannot apply this procedure that I am going to describe here. So what we can do, we can in a sense start with this initial algebroid E and restrict it only to C. It means that we will need C embedded in E. If we have this embedding, then we have a projection from E star to C star that will be needed. But we definitely need this metric because we need a complement also. We need to be able to write E as C plus an orthogonal complement, and then everything works. And the fact that we have to read it like that, and the fact that we have a restriction of the type of the Lagrangian, these two things are related closely. So I have not only the embedding, but also a projection, the orthogonal one, and then from this embedding and this projection, I may write down such a diagram which allows me to go using the tangent to the projection, the cotangent to the projection. I go then in this direction. Of course, the cotangent map to the projection is not really a map, but a relation. However, if you prescribe the point when you land, and so you start from C and land only over C, so then this is a map. So I go this way, but then I apply my algebroid, and then I go down by the tangent map of E star, and what comes out is another map similar to that, but what I'm going to lose here going around is the Jacobi identity. If I started with something that fulfills the Jacobi identity, and if C is not a subalgebroid, then this will be just a skew algebroid with no Jacobi identity. To see, okay, maybe we can look at the coordinate expression for a while, how it looks like. Then we will be able to see why we need this particular form of the Lagrangian. So I need coordinates that are adapted to the structure. So those vertical fiber coordinate I split into coordinates that are only in C and only in C orthogonal. Those orthogonality means that here I will also have two parts, something that the norm of the part of the velocity which is in C and the norm of the part of the velocity which is in C star, and they don't mix because they are orthogonal, those spaces. And then using coordinates, I can construct the coordinates everywhere on C and C star, starting from Q and Y, and then dualizing. So I also have those dual coordinates split into psi capital A and psi alpha, and I would like to kill these alphas everywhere. So what I do, I go up there and I see that I have already killed the alphas, yeah? So then I take a map to TE star. Since I killed the alphas, I don't have them here, and also whenever alpha appears here, it will also be killed. This splits. This last coordinate splits into two parts, something with only capital Latin and something with that can depend on beta. Yes, that can depend on Greek coordinates, but this part is killed by the projection here. So as long as I don't use any Lagrangian, this is very correct, and I apply, and I can construct such an epsilon, and it works. It is a skew algebroid. Those C's, since they are just part of structure functions of the initial algebroid, they lose this Jacobi identity. But the question is it useful? Yeah.
It could be easily explained for just Lie algebra. I have Lie algebra with metric and a vector subspace there. and I define a new bracket on the subspace. I take two vectors, the bracket, this usually goes out of the subspace, but I do the projection. So this is how this new bracket, of course, usually we don't have Jacobi identity any longer, yes, but this is still skew-symmetric.
So this is still a structure, but is this structure useful to really describe a system? So let us look at it like that. I have this mechanical Lagrangian, so I can use the variational principle. This is called the D'Alembert principle when we are forced to take into account the constraints. And I obtain, it is written here in the coordinates, I obtain Euler-Lagrange equation in such a form. The problem with this Euler-Lagrange equation is that it contains structure functions that depend only on things in C, but also there is this alpha here, and there is the differential of the Lagrangian in the direction which is perpendicular to the constraints. And in principle, it is not bad because nonholonomic constraints interact with the system. So they really, there is really a force coming from the constraint, and if the constraints are ideal, we assume that this force can be as big as we need it to keep the system along the constraint. So this is the thing that really should appear. It is okay. But in case when we have this mechanical Lagrangian, the part depending on velocities perpendicular to the constraints is separated from the part which is along the constraint. And as I said, those two sets of coordinates do not mix. So when I calculate this differential, I see that, this differential depends only on those y's, and since I have, since those y's are zero because I am along the constraints, then it means that this differential is zero. So in this differential is zero, then in practice, I don't have this part, and I can cancel it. And then I obtain exactly the equation that I would get using this skew algebroid structure. So the result is that in this particular case, for this particular type of a Lagrangian, I can just restrict my Lagrangian to the constraint, use the structure and get my equations. I may get my phase equations, and these phase equations will produce the correct Euler-Lagrange equations, and then will produce the correct solution. But this very much depends on the fact that this is of such a form. So, of course, there is a natural question, and what if it is not a mechanical Lagrangians? And we know there are examples of Lagrangians which are not mechanical. For example, if you switch on the magnetic field and you are and your particles or your bodies moving there are charged, then you will have a additional linear dependence on velocities, and you cannot do that. So then there is then there is a need to generalize still a little more to include magnetic force and gyroscopic force. Then if we want to produce phase equations, of course, still variational principle works. I mean, Euler-Lagrange equation you can get from variational principle, which is good because then you can check whenever you produce a kind of phase equation and you decide what is your phase space, then you can check if it is really what you need. So if you can check if the equations are correct, Euler-Lagrange equations are correct. So I claim that Dirac structure is something which is useful when you want to produce phase equations for systems which are not of this special mechanical type. And we pass to another generalization. If you want to know details on this example that I presented with mechanical Lagrangian, it is written in the paper by Janusz, Manuel de Leon, Juan Carlos Marrero, and Martin de Diego, with the citation here. I forgot about the example. There is the particular example of the particular mechanical system. I told you that we will be talking about skaters. So imagine I have a ice ring. On the ice ring there is the skate. The position of the skate is given by x and y, and the skate of course can rotate. And the skate can move only along the direction of its orientation. So I have constraints, and those constraints are non-holonomic. You can check it easily in a sense that this subbundle is not integrable. And I have a mechanical Lagrangian. Here I added gravitational force, because without gravitational force on the flat ice ring, nothing really happens. If you have some initial rotation and you have some initial velocity, you will just go in circle. And of course it is a valid solution, but nothing special. But funny thing happens if your ice ring is a little bit tilted, and what you will expect is that you will slide down, yeah? You won't. The result is if your ice ring is a little bit tilted and you have some initial rotational velocity, you will not slide down. You will go in a kind of cycloid motion. Depending on initial conditions, the Mathematica produced different fancy cycloids. Some of them are really cycloids, and some of them, if the initial conditions are correct, they start to somehow behave in such a way. Nevertheless, you will not slide. You will go in the perpendicular direction to the direction of your of the tilt of your ice ring. And then what we are going to do, we are going to add some charge to the skate, and we are going to put this all in the magnetic field. And no, at the very end you will see that I did it in a stupid way, but we will see it. Okay, so now we generalize ourselves a little bit more, and we will be working with Dirac structure, a special kind of a Dirac structure, linear one. We are all the times linear, so we consider linear constraints. Here we will also consider linear constraints, and there will be examples, this ice ring thing revisited with and without magnetic force. Okay, so what is the Dirac structure? First, the original definition, Dirac structure on a manifold. Then this manifold will be a total space of a vector bundle, but we start with just a manifold.
Dirac theory of constraints.
Yeah, so it has something, from the very beginning, it has something to do with constraints.
So you take the Whitney sum of the tangent bundle and the cotangent bundle. Some people call it generalized tangent. Some people call it Pontryagin because it has something to do with the control theory and Pontryagin principle. Although the name Pontryagin does not fit in this context at all. However, just the same bundle is used. In this bundle, we can consider a symmetric pairing of vector field and forms. You just mix them. So first form is evaluated on the second vector field and second form on the first vector field. This is a symmetric pairing. On sections of such bundle, there is the bracket called Dorfman bracket. in such a form. I have written the bracket for completeness, but I will not be using the bracket at all. Therefore, I don't enter to those discussions that there are two brackets, one of them antisymmetric, the other not, one of them Jacobi, the other not. Doesn't matter. For this thing, it doesn't matter. Of course, it matters. I mean, the bracket and the properties with respect to the bracket matter when you consider, again, the properties of the equations you obtain. Integrable or not, do you need integrable conditions, whatever. Then this matters. But for the process of generating the equations, it does not matter a lot.
Yeah, this is the bracket is related to the integrability condition.
So the original definition is like that an almost Dirac structure is a maximally isotropic subbundle of this bundle, maximally isotropic with respect to the pairing. If it is additionally close with respect to this bracket, it is called a Dirac structure. What we will be using are almost Dirac structures. And there are examples, several examples, canonical examples of Dirac structure. For example, take a bivector, take the map given by the bivector, and take this subbundle as a graph of this bivector. Then it is almost Dirac, and if this bivector is Dirac, then we get, the bivector is Poisson, then we get a Dirac structure. You see why I will be using Dirac structure as a generalization of the previous structures, because my algebroid was a certain kind of Poisson, therefore, or skew, or just a bivector. Then when I generalize, I will use more general Dirac structure. If you take a form to form, you also can get a map from this two form, and then you can take a graph of this two form, and again it is almost Dirac. This isotropic condition comes from the skew-symmetricity of the form, and it is Dirac when the form is closed. And again, this Dirac structure can generalize both Poisson or pre-symplectic, yeah, or just the two form. And there is another example. Take any distribution on regular distribution on n, and take as a subset, as a subbundle in our bundle, a sum of this distribution and its annihilator. What you get is again almost Dirac structure, and when this distribution is integrable, then this is the Dirac structure. And then we will be, in a sense, mixing those examples, starting from some bivector and adding some flavor of the distributional example to fit this into the constraint problem. Okay, so now we are going to make our Dirac structure, or almost Dirac structure, to be linear. Therefore, we take our manifold to be the total space of the dual of some vector bundle. In example, it will be just the cotangent bundle. And what is Dirac algebroid? Dirac algebroid is a linear, almost Dirac structure on E star. So what we add here is the regularity, is the linearity assumption. And linearity is usually expressed in some as being a morphism of some double vector bundle. Since we are here we are not talking about maps but about subbundles, the linearity means that this subbundle is not only a subbundle of this projection, but it is also a subbundle of the other projection. it is a double vector subbundle of the double vector bundle that appears as the space when we live in here. So to see that it is a double vector bundle, let us look at the two bundles we compose to get this one. There is tangent to E star, and there is a cotangent to E star. We add them. We require this to be, this is the generalization of the algebroid, so it has to be over the identity on E star. And initially our Dirac structure is a subbundle over E star. So then I get this subbundle over E star here. And on the other leg of this projection, what I get from the sum is the Whitney sum of E and Tm. And I get something in the core which appears to be okay, we will see. So for example, if my linear Dirac, almost Dirac structure comes from, say, algebroid, so from some Poisson, or not Poisson, from some bivector, then it is a graph of a map coming from bivector, then here I will have a graph of my anchor. And here I will have the annihilator of the graph of my anchor, because it appears from the antisymmetricity condition, I get that this core is the annihilator of the bundle here. In principle, double vector subbundle can be a subbundle over a submanifold on one side and also over a submanifold on the second side. But in the example, the submanifold here will be the full E star. But it can be, we can have something which is smaller here and smaller here. And it can also be, there can also be restrictions on the position. This all fits into the picture. How do we use this? I will not be going deep into the structure of those bundles, because then you write very long expressions in coordinates, which some are 0, some are not 0, and on the screen it is impossible to follow. So only the overview, how do you use this structure? So this is the diagram we used for algebroids. And this is the diagram we will use for Dirac algebroids. For true algebroids, we have maps here. And for Dirac algebroids, I will have a relation. The algebroid I got from lambda was a graph of this map. Here I have another subbundle, double vector the subbundle, the double vector, double subbundle. Oh, okay. I got entangled into those double things, but I can treat this subbundle of the Whitney sum of this and this as a relation between covectors and vectors. So instead, I can take a covector here and ask the question, what are vectors that are related to this particular covector? Since the Hamiltonian part is isomorphic to the Lagrangian part, I can always compose this relation with the isomorphism and get the Lagrangian relation. So here I work with relation instead of maps. And on the basis here, I will have also a relation that takes the role of rho. Here in algebroid case, I got a map, and in case of more general thing, I can have a relation. It is always over identity on E star, so if I start from some bundle, some subbundle, I stay on this subbundle. But then the structure works in the same way. So I can take a Hamiltonian. If it is over a subbundle, I generate a Lagrangian submanifold from the function and submanifold. It is possible. If it is over the whole T star E, as I wrote it here, no, it is yeah. So I generate a submanifold here, and then I look for vectors which are in relation with covectors that belong to this generated submanifold here. And on the other Lagrangian side, the same. I generate a submanifold here, and I look for vectors which are related with vectors that belong to that belong to T E star. And those vectors that belong to the T E star and are in the relation are my form my my first order differential equations, my phase equation. And this is a very general scheme. So let us look how this scheme works. This scheme was for the first time written in the paper by me and Janusz, Dirac, Algebroids in Lagrangian and Hamiltonian mechanics. We wrote this paper, and then we, in a sense, forgot about this. So we didn't really follow with, I don't know, calculating more examples, analyzing special cases, whatever. We just were happy that our scheme works. There are some examples in the paper, but there are of those general kind that sometimes when there is a theory and the professor is asked for examples, he says, of course, look, a differential calculus is an example. So I remember it was a real situation when Professor Vinogradov, you maybe know, some of you know the guy, or used to know the guy, because he's deceased now, and he was working on, at some point, at C-spectral sequences, something very, very general. And he was asked, okay, so this is very beautiful theory, but what are the examples? And he said, okay, the differential calculus is an example of my C-spectral theory. So, theory of partial differential equations. So this was, no, maybe not to that extreme, but these were the examples of a very general kind. And then a year ago or something like that, maybe I will move to, for a moment, to the very last slide. A year ago, I noticed on arXiv a paper, almost Poisson bracket for nonholonomic systems with gyroscopic terms and Hamiltonization. And I thought, okay, nonholonomic systems in general can be done with Dirac structures, so I should take a look and check what they did. And I've seen that what they did, they worked hard to produce some almost Poisson bracket that describes their system. Gyroscopic terms and magnetic terms are of the same type from the point of view of geometry. So we may also think on mathematics. And I thought that, okay, it was, no, I didn't like this example. This almost Poisson structure, I will tell you why I didn't like it. And I decided to check if it works with my or our Dirac structure. And it turns out that it really works, and I will show you how it works. So the Dirac structure we need for describing systems with constraints, non-holonomic constraints, and very general, with no restriction for the type of the Lagrangian that we use, can be constructed in the following way. For simplicity, I will start with canonical algebroid of the tangent bundle. And I have a constraints which are non-holonomic, so it is not a subalgebroid. What I'm going to do, I'm starting from this initial Dirac structure, canonical Dirac structure, and induce a Dirac algebroid by using this C. So what I do, I take, first I take this C and restrict my velocities only to this C. My initial Dirac structure is such that that here I have, this is a graph of symplectic form, yeah, the graph of symplectic form. So I have here whatever covector, and here I have only vectors that, oh, it is written here, sorry. So I take only vectors, only graph of the identity. So the same here and the same here. Whatever covector here, the graph of the identity here, and graph of my symplectic form, which in the language of Tulczyjew triple is the graph of this map beta m. It is in coordinates, it is written here. So you see that these coordinates are the same, and here are the same coordinates with the minus. This is that. So then what I do, I restrict to the constraints. So I take the graph of the identity, but only on constraints, and I denote it by delta. No, okay, but if I restrict only here, then my subbundle is of the wrong dimension. It is too small. So I have to enlarge the dimension a little bit in the vertical directions. What I do, I've written here in coordinates, I add the annihilator. The annihilator is in the core of this double vector bundle. Elements on the core of the double vector bundles can be added to elements of the total bundle without changing any of the projections. So I can easily smear this out in the vertical direction, adding this annihilator here. Then I have a proper dimension, and then this is still a linear subbundle, double vector subbundle, and then I have a Dirac, really Dirac structure, restricted to the constraints, and with the possibility, those vertical directions are those forces that come from the constraints. And adding whatever element of the annihilator, I allow these forces to be whatever, as strong and as I need to keep my system in the constraints. Here I have written the Dirac structure in the coordinates, and it is maybe not, I mean, if you do not follow with the construction of the coordinates, which on the screen is a little bit difficult, you don't really see what happens, but maybe we could a little bit discuss it. So here we are in T star M, and again, since my example will be with the mechanical system with the magnetic force. So I will have a metric there. Then it will be easier to use, again, coordinates adapted to C in such a way that I have a splitting into something which is in C and something which is orthogonal. Then I have a splitting of something which is in C star and something which is the annihilator of C star. Here we are in T star M with the splitting dual to the constraints and orthogonal. Here we are in Tm, and we have something which is along the constraints, and from this from the Dirac structure we get that perpendicular to the constraints are 0, and this also is continued here, so those alpha do not appear because they are 0. But here we have those vertical directions, and adding annihilator produces the result that at the very end I have something which is arbitrary. Here I have coordinates that are decided by the structure of my Dirac, of my initial algebroid with structure functions and an anchor. And here I have this perpendicular part, in a sense, is arbitrary. And now we can see how it works in examples. We will apply this to two types of now working on Hamiltonian side because it will be easier. Two types of Hamiltonians. The mechanical one, which has, again, kinetic energy, and since it is Hamiltonian, it has plus potential energy. And again, potential energy depends only on positions. And momenta written in these adapted coordinates are here. And again, they split into two parts. And there is mechanical Hamiltonian with magnetic force. Magnetic force is represented here by the magnetic potential. Magnetic potential is a one form on the space of positions, and this and when we write it on the Hamiltonian side, it comes with in the form of so-called minimal coupling. It means that our momenta are a little bit translated in the direction of this magnetic potential. So our momentum is a covector, our magnetic potential is also a covector, and this is how the Hamiltonian looks like. And again, we have a splitting between something which is along the constraints and something which is perpendicular constraints, and there can be some potential. But now it is not if you just expand it, you will see that it is not quadratic in those momenta, but there is also a linear part in the momenta. So it is not mechanical as it was previously. And I use this Dirac structure. I derive equation in general form. Equations on the phase space derived from the Dirac structure are the following. The kind that resembles a little bit this part from variational principle, and again there is a dependence on the perpendicular directions. And as I said, it is okay that this dependence appears here. It should appear. Here I have just the compatibility conditions coming from the fact that I used basis, which is adapted to constraints. As a matter of fact, this rho is just a matrix of coordinate changes. And since I have to be on the constraints, I get only part of the matrix here, restricted to the constraints. But this is the compatibility condition, the admissibility conditions here. And this the real equation is encoded here. And I have this arbitrarity in the direction perpendicular to the constraint. When I write those equations down for the mechanical Hamiltonian, which is here, what I get is, again, the fact that this part cancels. Again, why this cancels? No, because I have to be on the constraints, and this dependence has to be 0. So when I differentiate it, again, I get the fact that this being 0 means that that the momentum with betas also is 0, and this part cancels, and I come back to the situation that I described using skew algebroid. So in a sense, this more general structure gives me the same answer. And however, initially I have my equation on the whole E star, on the whole T star M. Then there is the integrability condition written here from this fact that the differential with the of Hamiltonian in the directions perpendicular to the constraints has to be 0. I get the compatibility. I get that my phase space is really C star. So the integrable part of this equation stays on the E star, and my phase curves will lie on the E star. So effectively, if this has to be 0, then this arbitrarity doesn't matter, because it means that C dot also with beta, so perpendicular to the constraint, has to be 0, and we stay on C star. And nothing additional happens, and it is okay, because we knew that those previous equations were correct, so we should get the same using this structure, and we get the same. But then what happens when there is the magnetic term? When there is the magnetic term, this condition does not give me Xi beta equal to 0, but gives me that Xi beta should be equal to this magnetic potential. Then, of course, I again have some integrability conditions that prescribes how Xi dot behaves, and this part of the equation is not cancelled, but it appears here. It is there, and it should be there, because this says how are the forces that are given that we got from the constraints. And in principle, we cannot we cannot restrict our Hamiltonian only to the constraints, in a sense, to C star. But we can get this equation restricted to the constraint to C star translated a little bit, translated by the part of our magnetic potential. But the problem is that this magnetic potential is the part of the Hamiltonian. So in a sense, if we want to write it only on the dual of the constraint, we can do it, and those Spanish people did do it, but they have to include in their Poisson structure an information which is part of the Hamiltonian. So not coming only from constraints, but coming also from the Hamiltonian. So the structure depends on the Hamiltonian that we use. And this is the part that I didn't like. I like my structure to be general, to work for all possible Lagrangians or Hamiltonians. And then the result that I have some effective phase space, which is in this case an affine subbundle of the cotangent bundle, which is dual to constraint translated a little bit. So not the dual is a linear subbundle, and translated a little bit is an affine subbundle. Then I get something which is I can use this structure for whatever potential I put here, and I don't need to change the structure with every change of the potential. And now, why my example with charged skater was stupid? It was stupid because I put the charge in the center of the skate. So now imagine, if the charge is in the center of the skate, this charge does not affect the rotation at all, because the Lorentz force has this property that it is always perpendicular to the velocity. So the only velocity this charge is moving with is along the constraints. So the magnetic force is perpendicular to the constraints, so it doesn't affect anything. Of course, the equations that you calculate look complicated because there is this magnetic field there. However, if you solve those equations, what you see is nothing changed. Yeah, I put some initial conditions to the Mathematica, and it produced a curve like that, which is one particular example of the curves that we seen there. But when you really calculate things, when you are thinking about the structures, sometimes you misthink, maybe not you, but I, miss details on the examples. And I noticed this fact that this is a stupid example only at the very end when I looked at the solution and said, well, nothing happened, so what? And I started to think why. And then I thought, okay, no, because just 2 little dimensions. I wanted to have my example simple in 3 dimensions. Yeah, there is just no room for this magnetic force to be really visible because it is always perpendicular to the... I may change it. So if you take a skate and put the charge a little bit in a distance from the middle, and then it will work. And this is the example that I have to calculate to really see the difference in trajectories. But I understood it a little bit too late. Okay, so this is, I suppose, all this slide we have seen, and this is the last slide. Thank you very much. The lady here is the lady that accompanies us
in the main lecture room on the Faculty of Physics of the University of Warsaw. Nobody knows how she appeared there, but she's there.
Memento mori.
Memento mori.
Is it a special underlying electric charge?
Possibly. So that's all. Thank you.